Yes, thanks, Luke, for the introduction and for inviting me and the opportunity to talk about this. In fact, he was mentioning Baran plateaus, and the actual connection is we had to learn a bunch of representation theory to prove results in Baran plateau and understand the scaling of these variational algorithms. And now there's a kind of clear understanding. We thought, what else can we do with representation theory? And this is a little bit of what we've been cooking in the last months, years. So, okay. Today I'm gonna talk about this work out like last summer with in collaboration with Wojciech Havlicek from IBM. And as Luke was saying, these are quantum algorithms for representation theoretic multiplicities. More precisely, we give quantum algorithms that are able to compute certain coefficients that are relevant in representation theory, but also in algebraic combinatorics and geometric complexity theory. And the way we are able to compute these coefficients is by encoding them as Fourier components of certain functions, which functions we're able to build as quantum states, and then we're able to apply quantum algorithms that are able to extract these Fourier components. And when I say Fourier components, I mean Fourier components in a generalized way, Fourier components over certain groups that are not the typical abelian one, but in this case, it's gonna be symmetric group. We've long known of efficient Fourier transforms over the symmetric group that, in a sense, are parallel to the celebrated quantum Fourier transforms that power Shor's algorithm and period finding algorithms. But unlike the abelian quantum Fourier transforms, the non-abelian quantum Fourier transforms, unfortunately, don't have found a lot of application yet. And yeah, this is an attempt to give them an opportunity. So our algorithms are efficient in regimes where no classical algorithms were at the time we put the paper out. Couple months after, we got the attention of certain algebraic combinatorists who developed new classical algorithms that work in the same regime as our quantum algorithms, yet with a complexity gap. There's still, with respect to the best classical algorithms we know, there is still a quantum speedup that is shown down here, and we will discuss a little bit in the end. To be able to introduce the results, we'll have to build up concepts in representation theory and quantum computing, and I'll try to assume no prior knowledge. And I think it's a great opportunity to try to refresh or learn new stuff. Even if I think, like, most importantly, if I am able to motivate the learning of representation theory, I think it's applicable to like a huge amount of work. And if you find an application, that would be a triumph for my presentation. Okay, so let's start. We will consider a quantum computer. What's a quantum computer? It's an ideally closed many-body quantum system over which we have a remarkable amount of control, in the sense that we can maintain its coherence, we can implement operations between the different qubits, let's say. And of course, we will constrain to polynomially many operations. Those are the quantum circuits that will be relevant for us. So this is the circuit model of quantum computing. We have wires that represent the qubits. Each qubit is associated with a two-dimensional complex vector space. And then we put these boxes that represent gates between the qubits. And these gates, for example, between two qubits are unitaries in C4, and we will compose them to create basically larger unitaries. Let's say we'll A, B, C, these gates, we compose them to some U in U2 to the n. Of course, we will never be able to achieve any U in 2 to the n. We would need exponential number of gates to get the full unitary group. But we still think that polynomially sized quantum circuits have interesting power. After applying gates and initial state, we make a measurement. This outputs an outcome, which is a bit string, an n-bit string, that happens with certain probability that is just the trace of the evolved initial state and the projector into such computational state. The name of the game will be to engineer these circuits to access samples X from this probability distribution that allow us to solve some interesting problem. And as I said, in my particular case, I will encode into this probability distribution certain relevant coefficients. So something I'd like to note is that quantum circuits reduce to classical reversible circuits when we restrict our gates to be the NOT, local gate, the C-NOT, interacting gate between two bits, and Toffoli gates. In that case, all of the classical reversible circuits compile permutation matrices, essentially, which is a strict subgroup of the full unitary group on 2 to the n complex dimensional vector space. And of course, the reason we are here, we attend quantum computing talks like this one, is because we believe quantum circuits to be strictly more powerful than classical circuits. Yet, we are trying to still understand what is the power of quantum circuits. This is still an open question. So quantum states are 2 to the n dimensional complex vectors, and quantum circuits are 2 to the n by 2 to the n unitary matrices. Then I raise the question, is quantum computing just doing high dimensional linear algebra? A priori, yes, but my argument here will be that we don't care about all high dimensional linear transformations, but instead for certain very structured subsets that arise from nonlinear algebraic structures that are encoded or embedded into this high dimensional space of linear transformations. And that's where representation theory will enter the picture. Representation theory is a bridge between abstract algebra and linear algebra. It represents groups as sets of linear operators, better be invertible, and yes, and essentially it's representations that, group representations that are related to symmetry, as we will see soon. So let's introduce what a group is. It's a set together with an associative multiplication that assigns a pair of elements with a third element in the set. There is an element in the set that is the identity E, such that when we multiply any element with E, either from the left or from the right, we get that element back. Every element has an inverse G minus 1, such that when we compose, we get the identity. And yes, those are the properties of a group. And now we will give examples. So for example, the symmetric group is given an arbitrary set X, is the set of bijections from X to X. So if X has n elements, doesn't matter what those elements are, this will be the permutation of all of those elements. Oh, yes, there we go. So for example, the permutation group of 3 elements is this set of 6 elements that provide all of the ways of bijectively mapping 1, 2, 3 to 1, 2, 3. So I can either apply the identity bijection, I can apply the a transposition of the first two elements and leave the third element untouched, and so on and so on. And one can check that if I define the operation for two group elements to be concatenation of these diagrams, then this thing is a group. So for example, I bring 2, 3, and 1, 2, and I compose them, and you can see that 1 goes to 1, but then goes to 2, the 2 goes to 3, and then keeps going to 3, and 3 goes to 2, and then goes to 1. So this is the diagram on the right, that is the 3-cycle 1, 2, 3. The composition of two transpositions or two cycles give me a 3-cycle. Okay. I just say there that there are other examples. Some subgroups of the symmetric group are the alternating group and the cyclic group. It's the cyclic group, for example, is generated by a K-cycle. If I take K-cycle and I compose with itself, I get a K different elements, subset of the symmetric group that are closed, so it's a subgroup. Please interrupt me if we need any questions. So moving on, I wanted to give an example of a set that is not finite, but infinite. So in this case, the unitary group is the infinite set given by the subset of all D by D matrices that are unitary. A matrix is unitary whenever U times U dagger, so U times its complex conjugate, is the identity. This is equivalent to asking that the determinant of the matrix is a phase or a complex number with unit modulus. And this is a subset of the set of all matrices, but also a subset of the set of invertible matrices, since the invertible matrices are those that have non-zero determinant. And in this case, the determinant is not only non-zero, but is of modulus 1. Another example would be a subgroup of these things, which are the determinant being exactly 1, not of modulus 1. And these are the special unitary matrices. Let's give examples. So the special unitary matrix on dimension 2, here I give 4 instances. You may recognize these things as the Pauli matrices, but with an I there. Okay, so identity IX, IY, IZ, they're all special unitary matrices. And I guess you could ask, are they, for example, instead the I times identity, which is not in the above set, is not there because it's not unitary. It's special unitary. Down here, I give a fast way of checking what's going to be special and what not. So the determinant of IA is I to the n, where n is the dimension of A times the determinant of A. Here the dimensions are 2, and all of the Pauli matrices have determinant -1. So I will need to have an I there for it to be special. That's why they appear with an I there. Maybe we can move on. For example, we can check special unitary matrices composed to special unitary matrices. And yeah, I'll leave that to check later. We have specified how groups act on themselves via this multiplication that you need to define. The action of groups can be extended to action of vector spaces by mapping group elements to linear operators on the vector space. And that's what representations do. So representations are these maps that assign group elements to elements of another group, in this case, the general linear group. As I mentioned before, this is the group of invertible matrices on a vector space B. So you can think of the matrices of dimension of B times dimension of B that have non-zero determinants. That thing is a group, and a representation, general representation, maps any abstract group to elements of this group. And the reason is that this is among the most general things that you can get group to go to, because you need to have inverses. So, but not any map will be a representation. What you need to ask the representation is to satisfy the equation 1, which is essentially that if you first map both elements and then take the product of matrices, or you first use the group operation in the abstract world and then you apply the map into a matrix, those two things have to be the same. And the technical name for this is a group homomorphism, which means that it's structure preserving map. And less technically, you can think of a group representation as being a subset of either the unitaries or this kind of GLB matrices, the image of the map, that is a group isomorphic to the domain of R, which is the group. And the reason it's isomorphic is via this structure preserving constraint. So one other definition is that I will say a representation is unitary if its image is contained in the unitary group of B, rather than on all GLB. And every group that I will refer to in this talk will be either finite or compact, and the representations of finite and compact groups are equivalent to unitaries. So all representations are unitary. So every time I will assume that my representations that appear go from G to unitary group, so unitary matrices. We call vector spaces that support group representations group modules. So examples of representations are the standard representation for the special unitary group, for example, which is mapping D by D special unitary matrices to themselves, because they are already matrices. Instead, symmetric groups are not matrices in the abstract group, but they will be mapped to matrices. And we, for example, one representation possible is the action of symmetric group on n-dimensional vector space, where the group permutes the basis vectors, n basis vectors. So the representation will be n by n permutation matrices, the set of all of them. There's one for each group element, n factorial many. Instead, I can think of the action on another vector space, which is the tensor product of n sub-vector spaces. I take, in this case, let's take the qubits, for example, C2. I tensor n of them, and I demand that the group acts by permuting these subsystems. Oh, God. And now the image of the representation, so there are 2 to the n by 2 to the n permutation matrices, but not all of them. Only n factorial out of the 2 to the n factorial many 2 to the n by 2 to the n permutation matrices, those induced from the permutations of qubits. Similarly, I can think of the symmetric group acting on itself, essentially. So acting on a vector space of dimension n factorial, where each direction is a permutation, and it will act with the circ operation, the group operation, basically. And again, this would be a subset of the n factorial by n factorial permutation matrices, but only n factorial out of the n factorial many. I hope this is not too confusing. It's just some examples. Here I want to give a little bit of intuition of why group representations are relevant, in the sense that they describe symmetry, which are subsets of linear transformations that leave vectors invariant. So for example, you may have heard that the GHZ state, which is an interesting state for entanglement theory, is invariant under permutations. You can see it right away, because if I permute the qubits, nothing will happen. But it's not SN invariant, it's invariant under the specific representation of Sn that acts by permuting qubits. I could think of another way of symmetric group to act on this vector space where this n qubit state live, and it will not be invariant. So yes. And similarly, I wanted to give the example of the SU2 invariance of isotropic Heisenberg interactions. And again, like there is an action for, first I give you a vector, and now I give you a linear operator, which is a vector in the space of the vector space of linear operators. And the way that the group will act here is by conjugation. And still down here, I'm showing that the way the unitary group is represented here is by U tensor n. And when U tensor n conjugates this three-dimensional vector of spin, basically xi, yi, and zi, it acts like a 3x3 matrix, invertible matrix M, which depends on U. And since the interaction is a dot product between two three-dimensional vectors, it doesn't depend on U. That's why Heisenberg interactions are SU2 invariant. But they are not invariant under SU2 abstractly. They're invariant under this specific representation of SU2. Okay, moving on, we need to introduce what irreducible representations are. And essentially, they are the atoms of representations. They are the building blocks in the sense that, let's first define what an irreducible representation is a representation such that there are no subspaces W of B that are invariant for the action of G. So just an example to introduce this concept, let's come back to the first action of Sn on n-dimensional vector space that I introduced. These are the n by n permutation matrices. Here are two of them. I ask if this is an irreducible representation. Again, irreducible means that I cannot find a subspace of C4 that will be invariant under the action of all permutations. The answer is no, it's not irreducible because here's a subspace that is invariant. The vector, the line of the 1, 1, 1, 1 vector. Yet, if I take this subspace and its orthogonal complement, one can check that these two are irreducible. And we will come back to this later when we know more about irreducible representations of Sn. But as I was saying, the reason why I'm talking about irreducible representations is because they have this property that any representation has a unique decomposition into irreducible representations. More precisely, there is a basis in which the vector space now looks as a direct sum of sub-vector spaces B alpha G, which I will call irreducible submodules, that are repeated a number of times. Here I'm using M alpha, which is the number of times this irreducible representation appears in B. Alpha will be a label that will be assigned to different inequivalent irreducible representations. And yeah, maybe, yes, this, in a sense, the fact that you can always find a unique decomposition of a representation into reducibles reminds me a lot of factoring, and I will try to argue in the discussion how our algorithm resembles factoring in a way. So in this basis that diagonalizes the group action, the group matrices are now block diagonal, and they have, for each RG, there will be blocks that are exactly copied, repeated a number of times, M alpha, and I will call D alpha by D alpha the size of these blocks. And something to note is that abelian groups, all irreducible representations are one-dimensional, and therefore, in this basis that diagonalizes, block diagonalizes the group action, it's actually diagonalizing the group action because the blocks are now one by one, so it's just a diagonal, which is basically a spectrum that is repeated. And for reasons that will become evident later, I will call the basis where this happens the Fourier basis, the basis where the representation looks diagonal or as diagonal as possible. Okay, so the representation theory of the symmetric group, we first need to introduce conjugacy classes, which are subsets of the group that are the orbit of a group element under conjugation by all of the group. Oh, yes. So let's look at how conjugacy classes look for the case of the symmetric group. So take any permutation and decompose it into disjoint cycles. It turns out that since the cycles are disjoint, it doesn't matter if you reorder the cycles. And therefore, you can always choose to think of larger cycles first. So in this case, I have a 3 cycle, 1, 2, 3 is a 3 cycle, and 2, 4, 7, 8, and 6 is a 3 cycle, a 2 cycle, a 2 cycle, and a 1 cycle. So I can represent this as a sequence of positive integers that are weakly decreasing. They're ordered, the largest first, and the size of the cycles, if you add up, it will add up to the n, which is the size of the set the symmetric group acts on, of course. So there are partitions of n. A partition is this concept of a weakly decreasing sequence of positive integers. Therefore, we can use partitions of n to label the cycle type of any permutation of n. And we can depict these things graphically using something called Young diagrams, that is just boxes, one for each element, 1 to n, and that are left justified and such that the rows are always weakly decreasing the size of the rows. So the partition of 4 being 4, I just depict as 4 boxes as a row. The partition of 4 that is 3 plus 1, I depict it as 3 boxes and 1 box below, and so on and so on. I always left justify the boxes. And on the right, I am giving you a representative element of such conjugacy class. So in particular, the diagram that is 1, 1, 1, 1 corresponds to 4 1 cycles, and therefore it's just the identity permutation, which is its own conjugacy class, because if you conjugate the identity, you always get the identity because everything commutes with the identity. Okay, so permutations can be associated partitions of n that encode its cycle type. It's not hard to see that conjugation will preserve cycle type. And moreover, it will produce all other elements with the same cycle type. Therefore, we can use cycle type to label conjugacy classes. And we can break down, since conjugacy classes decompose a group into disjoint subsets, the conjugacy classes, I can now decompose, for example, S3 into sets that are labeled by the 3 partitions of 3. 3, 2, 1, and 1, 1, 1. Okay, all of this is to now say that since irreducible representations for the groups that I am considering, that are finite groups and compact groups, are one-to-one corresponded with conjugacy classes, and I know that partitions label conjugacy classes, then I can use partitions to also parameterize irreps, irreducible representations of the symmetric group. That is, for any representation of the symmetric group, R over some vector space H, I can break the vector space. There is some basis in which the vector space looks like a block diagonal sum of these V lambda Sn, which are the irreducible ones. Lambda is a partition of n, 10 times repeated a number of times. It could be number of times, could be 0, but this is a formal expression for any group module of Sn. Partitions are what labels the conjugacy classes and the irreducible representations. So coming back, there has to be some partitions. If I claimed before that this example, the S4 acting on C4, was breaking into W and W perp, which are irreps. Each of these W and W perp must be associated with certain partitions of 4. And here are the partitions of 4 that are associated to each, 4 and 3, 1. So again, here you have to believe me, there's not a lot of time to deriving this, but it's just an example. We move on to the representation theory of the unitary group. Let's consider the group module that is the standard representation which we already introduced, which is unitary group of D by D matrices acting as D by D matrices on the D by D dimensional vector space, complex vector space. Now, suppose we take the tensor square of B. This is, again, a representation for the symmetric group, for the unitary group, and it decomposes into 2 irreducible representations, which are the symmetric and the alternating subspaces of B, which I define here. And these 2 are irreducible representations associated with these 2 partitions. I am already saying that partitions will also label irreps of the symmetric of the unitary group. So this is the formal statement. Again, I will not explain why. Maybe some flavor will happen later, but it turns out that we can label all polynomial irreducible representations of the unitary groups also using partitions of n, but now n is not fixed, it's not constrained to be like the degree of the group like it was with the Sen. Now the number of boxes can be arbitrarily large. They will still label SUD irreps, but what you need to constrain is the number of rows. It has to be less or equal than D. So in particular, if we consider 2-row partitions, this will be irreps of the SU2, and AKA also known as spin irreps. So I need to tell you how to get the spin out of a partition of 2 rows. If you call lambda1 and lambda2 the length of the rows, the spin is just lambda1 minus lambda2 over 2. It's the difference of the 2 rows divided by 2. You can already see that if n is even, then this difference will always be even too, and therefore you will have integer spins. And conversely, if n is odd, the difference is half integer value, and you will have half integer spin. So this already explains if you take 2 spin 1/2 and you tensor them, you get spin 1 and spin 0. But if you tensor 3 spin 1/2, you get half integer and so on. And this is an example. Here I would take 4 spin 1/2 and I tensor them. And this will explain, here are the partitions of 4 that you can get. So again, the theory says, I can, if you fix n to be 4, you need to look at the partitions with 2 rows. There are 3 partitions of 4 with 2 rows, those ones there. Therefore, those are the spin irreps that appear in the tensor of 4 spin 1/2. And this corresponds to spin 2, 1, and 0. Of course, if you add up the dimensions of the irreducible representations, these are spin 3/2. Spin 2 has dimension 2 times 2 plus 1, 5. So 5, 3, and 1. If you add up that, is 9, but 4 spins have dimension 16. So there's some dimension lacking. What's happening is that they are appearing more than once. Okay. So how many times they appear? Okay, first I will claim that if lambda is a partition of n, the corresponding SUD irrep B lambda will appear at least once in the subspace of the standard representation tensor n, where n is the number of boxes. Again, like imagine your favorite arrange of boxes. Then you know that this labels a irreducible representation of the unitary group, and moreover, you know that it will be a subspace. If you count the number of boxes, you tensor the standard representation, that number of boxes many times, it will appear as a subspace, this irrep. And there's something called Schur-Weil duality that states that not only all lambda appear, but the number of times they appear is the dimension of lambda being of the irreducible representation of the symmetric group appearing at the same time. So irrep of SUD lambda appears dimension of the irrep of the symmetric group many times. This is not super important. I think it's for this talk, but I think it's very interesting statement. Okay. Let's do an example of why we are going into irreducible representations and irreducible decompositions, and how is this related with Fourier analysis. So everyone knows the discrete Fourier transform, right? Let's state it in a general way here. So again, H is a G module. There is a unitary that block diagonalizes H. Let's see why this unitary, we will call it a Fourier transform. So we consider the cyclic group. So it's the subgroup of Sn generated by an n cycle. Alternatively, you can just think that it's the set of n numbers, n integers, modulo addition under addition modulo n. And consider the cyclic group and its action on a group module that is the group algebra. It's the regular representation that I already introduced. So it's the group acting on itself. So Cn on Cn. For example, this is how the matrices look. They will map the ith element in the group to I plus u. They will shift it by u units. The discrete Fourier transform maps this discrete position basis of the group to something we could call discrete momentum basis, j hat, such that, well, here's the expression, such that when the group now acts on this j hat basis, nothing happens or at least like it's just a phase. It doesn't kind of change to another basis. It's a one-dimensional subspace. We saw one-dimensional subspace, like abelian groups like this one have irreducible representations that are one-dimensional, all of them. So what I'm saying is j hat is an irreducible representation, or spans a one-dimensional irreducible representation. And now I am writing the whole group, the whole group algebra B as a direct sum of all Vj's, which each of them are spans by these j hat things. So in a sense, what I'm trying to point out here is that the discrete Fourier transform, in a sense, is just block diagonalizing the action. Well, not block because it's abelian, but diagonalizing the action of the translation group. Now I want to touch a little bit with quantum Fourier transforms. So the idea is that if you want to compile discrete Fourier transform classically and naively is n squared cost, but there's an optimization called FFT that works in n log n cost. And the DFT is a unitary matrix, so one can compile it into a quantum circuit. A priori, that doesn't say much, but not only we can compile it, but the compilation is very efficient. It's log n gates that we need. So, and this is what's called the quantum Fourier transform. It's just, again, it's just a compilation of the unitary matrix that maps discrete position to discrete momentum basis. And this quantum speedup in rotating discrete position to discrete momentum, or this quantum speedup in accessing the basis where the shift group is diagonal, is fundamental component of some of the most successful quantum algorithms known to date. For example, period finding, which is an instance of the hidden subgroup problem, where you have a function that's hiding function defined on the group to a set of cosets that is hiding a string, and you are hiding in the sense that f of x and f of s plus x is the same, but you don't know what s is, and you're asked to find s. And a priori, this classically you need to kind of guess until you find s, evaluate f many, many times of or the order of s times, but quantumly, and S is of order of n. So linear many evaluations. Instead, with short period finding algorithm, you can do this in log n squared time. And period finding is a fundamental component of the following algorithm I'm presenting, which is factoring. You're given an integer n, and you're asked to find the unique set of positive integers, non-negative integers, mi, such that n is decomposed into primes like this. And again, best classical algorithms run superpolynomially in log n, while quantum algorithms run like log n squared. And here I ask, why is this so special? What's so special about C, the cyclic group? And I claim there's not much, and we should be able to find successful quantum algorithms based on compiling the DFT over other finite groups, for example, the symmetric group. So a little bit of perspective. What's the Fourier transform? What was the Fourier transform? I presented one specific Fourier transform, what was the discrete Fourier transform. So Fourier transform was simply finding the components of S in some special basis that I called the Fourier basis. Something similar would happen, and what's the application of this? If you have some signal that is sufficiently smooth, you can cut the higher harmonics, right? I think this is the idea behind Fourier analysis. Similarly, if you had a function on the sphere, and if the function of the sphere wasn't oscillating too much, you could expand it into low order or low frequency spherical harmonics. So there's we're starting to get a flavor of Fourier transforms over other groups than the abelian one. So I will define what I mean by a Fourier transform over an arbitrary group representation. Is just take an arbitrary group module H and assign any function from H to the complex numbers. You can represent as a vector in H by evaluating the function on a basis of H and linearly combining these things. The Fourier basis is nothing but the basis in which H gets its exposed. This equation, we showed them many times, like this, the one that where H is broken into irreducible representations. So I will call this the Fourier basis. And in general, from inspection of this equation, the Fourier basis would look like, can be labeled by tuples here. Alpha, the irreducible representation, I alpha, something spanning a basis for each irrep B alpha, and J alpha, something going along the copies of alpha in H. So in this case, the Fourier transform of F will be another C-valued vector hat F in H with coefficients given by the inner product of F with the Fourier basis, essentially. This is what I was saying in the previous slide, motivation, but this is exactly it. Take your favorite function, encode it into this vector, and then take the components of these vectors in the Fourier basis. So a specific choice of group module H could be the group algebra, G acting on G, basically. So classical algorithms to perform this Fourier transform or to diagonalize this H run in order of H time. Instead, a quantum version can sometimes do exponentially better, like we saw it did for the cyclic group. So in order poly of log of G instead of order G. So how do we work out with quantum Fourier transforms is we treat F and F hat as quantum states in this module H, and we implement a quantum circuit we call UQFT that takes group basis to the Fourier basis. thus encoding, we can access the matrix elements of the Fourier transform by encoding F as a quantum state and applying this circuit and measuring, okay, sampling from this in this Fourier basis. As I was saying, quantum circuits compiling the Fourier transform over regular reps are known for groups like the symmetric group and several other subgroups. Here are some references. And instead, going forward, we not always care about the regular rep, right? As I was saying at some point, symmetry is not something about the groups, but it's about group reps. And we may be interested in certain group representation that is not the regular one. So what can we do in that case? We don't have, we can, like, at least we could frame a black box, which I call here RQFT or HQFT, for an arbitrary H that block diagonalizes this thing. And that would be great. But the thing is, finding circuit compilations of other than regular reps is more challenging. It has happened. And here I give a good example down there. The quantum Schur transform is an example of an efficient quantum circuit block diagonalizing the non-regular representation of Sn on an n-qubit system by permuting them, the one I showed you before. So there are examples where we did find quantum circuits block diagonalizing other than regular reps, but it's less common or harder. But suppose I just care about very arbitrary rep and I don't care about just full transform. What I want to do is something I would call Fourier sample, and not Fourier sample fully, but Fourier sample weakly. And by weakly, I mean I only care to measure the irrep labels alpha, rather than the full tuple alpha, I alpha, J alpha. If all I need is weak Fourier samplings, so yeah, let's discuss a little bit. You would have an initial state, and what you want is to sample alpha with a probability P alpha that is the trace of rho with pi alpha, the projector onto the isotypic subspace of type alpha. So as I was saying, if you consider rho to be your encoded function, this would give you the component on all of the Fourier components that are of the type alpha, essentially. And it turns out one doesn't need the full quantum Fourier transform in that case, the full Fourier transform. It's enough to have Fourier transform over the regular rep and a controlled operation. So what you do is you entangle yourself with another ancilla register where you have a regular rep, and then you apply the transform that you know how to compile in the regular rep. And by then measuring, as I'm showing here on the right, again, you have CG is a regular rep, H is an arbitrary rep. You apply an entangling operation that is the control action of, you control on group elements, and then you apply the group representation. And then you apply the Fourier transform on the regular rep that you know how to use, how to compile. Then you measure on the irrep register, and the probability of sampling alpha is exactly the same as if you had implemented this black box and measured alpha. So this is a way of going around. Yes? Yeah, exactly. So you only care about the probability distribution of alpha. This is what you wanted in the. So what I'm saying is, look at the thing on the left. The thing on the left is you have some state in H. Then you apply the circuit that compiles this block diagonalizing thing, and then you measure the alpha register. Measuring alpha register is accessing samples of alpha from a given probability distribution. What I'm telling you is you can get the exactly the same samples. You're doing a very different circuit. That's what Adam Harrow gave in his thesis. It's called generalized phase estimation. And yeah, basically, again, I will repeat, is you can get samples alpha according to to basically the component of the initial state in this whole isotypic alpha by just using an ancilla and applying controlled operations and then doing the QFT in the ancilla. It's very handy, and this would be like fundamental in our work, which I arrived at the slide. We're doing good of time. So recall there is a unique decomposition of any module into irreducible representations. And in this work, we will give a quantum algorithm to compute these multiplicities. Note that this resembles factoring. Remember, if I give you an integer, you decompose it into primes. Here I give you a representation, you decompose it into irreducible representations. And how does our algorithm work? It's the following 3 steps. Step 1, initialize a maximally mixed state over the group representation. Step 2, apply generalized phase estimation, which I just described, obtaining outcome alpha with this probability, right? Since you initialize the maximally mixed, then you get just the trace of pi alpha. So that's just the dimension of the irreducible alpha times the multiplicity of alpha divided by the dimension of the full module. So again, you sample alpha, and by sampling alpha, then you can do then you can record how many times you sampled alpha, and then you can estimate what this probability is. And then, if you know how to compute d alpha and dh, you can multiply by the alpha the probability that you estimate by the alpha and dh, and solve for mult. And the number of times you need to repeat this to get good precision in mult is order dh over d alpha squared. So a priori, this looks very simple, but the art is in finding a relevant mult to compute and efficient ways to initialize the maximally mixed state in H and implementing GPE. So here I will specify as a family of group modules that are relevant and where we can give a concise way of preparing these maximally mixed states and implementing GP, which is consider G to be a subgroup of some larger ambient group S, both being finite groups. And let's use alpha to label the G reps, as I've been doing the whole talk, and let's introduce this new gamma to label S reps. Any S module, B, let's call it, is trivially a G module if we act with the subgroup. So for any supergroup, a module for a supergroup, if I just restrict to a subgroup, this is still a module. And moreover, irreducible modules of the larger group lead to, in general, reducible modules of the smaller group. This is kind of natural to think. Like something that was irreducible, if I act with less elements, maybe it breaks into more than one irreducible subspace. So equation 12 shows how irrep gamma of S breaks down into G irreps alpha, well, with certain multiplicities, mult alpha in the restriction of gamma. So this mult alpha in the restriction of gamma is the multiplicities we will aim at. And here is the algorithm. You need to prepare a maximally mixed state on irrep gamma. That's the first thing you need to do. So what you do is you take a group algebra register for S, because the group algebra of S contains all irreps. So you can certainly find gamma inside of this register. And the way you prepare a projector into gamma, a maximally mixed state into gamma, is to apply the S QFT in reverse. So remember, the QFT takes module to irreps. So if I apply it in reverse, I can start with these 3 registers. One labels irreps, the second label, so the first one labels irrep, the second has like the actual basis of the irrep, and the third one has copies. So I can just initialize a projector into the irrep I want. then a maximally mixed state in the irrep basis, and then just a projector into the copy I want. Any copy will do the same, and I apply the QFT in reverse, and therefore I get rho gamma, which is my normalized projector into the irrep. And then I go to the right, and I have an ancilla that is CG, the subgroup G register. I initialize a uniform superposition. I apply the control action, this entangling thing. I apply GPE, basically. When I apply GPE, I will get samples alpha according to the distribution that I already discussed, which is here. It's proportional to the multiplicity I care for. If I know how to compute d gamma and d alpha, I just need to collect samples. And the number of samples that I need to collect is d gamma over d alpha squared. Remember, if I make the error sufficiently small, say less than a half, I am done because these things are integers. So if I estimate to precision 1/2, it's okay. And yeah, so the question is, okay, so far, yeah, tell me what this is interesting for. When is mult alpha in gamma interesting? And a good example would be the following. Take S, the ambient group, to be 2 copies, so the direct product group of Sn with Sn. So this is a group, this is a finite group. It has n factorial square dimension, and it's given by pairs of two permutations. And in fact, it has a subgroup, which is this diagonal pair of permutations, say GG, which is isomorphic to Sn inside of S. An irrep gamma of this S is just a pair of partitions because you're just giving one irrep for each of the two Sn groups in S, basically. And if you now consider the restriction to the symmetric group inside of the direct product of two symmetric groups, by definition, now is a representation for Sn. Therefore, it has to break into Sn irreps, lambda, partition of n, and the multiplicity that arises from this breaking they are known as Kronecker coefficients. And Kronecker coefficients, computing Kronecker coefficients is a fundamental and notoriously difficult problem. As I was saying in the introduction, these are very interesting coefficients. They were introduced in the 1930s. They were used as generalizing Littlewood-Richardson coefficients, which record the appearance of unitary group irreps in the tensor of a pair of them. If you remember, we were tensoring the unitary group standard rep with itself many times, and we saw how irreps appeared. Well, you can ask the question, if I tensor two unitary groups reps, how many times would a third appear? And these are Littlewood-Richardson coefficients. It turns out that these Littlewood-Richardson coefficients have combinatorial formulas. They count, there are some combinatorial objects that they count, but instead, if you define the same kind of multiplicity coefficient, but for the symmetric group, these Kronecker coefficients, although being positive or non-negative integers, there is no set of objects that they match, that they count. And it's been an open question for 85 years of study, like, can we find something that these things are counting? It's still an open question and very relevant to say, to put Kroneckers into sharp P or not. Recently, there was a quantum version of this question, and they were able to put Kroneckers into sharp BQP, which is the quantum version of sharp P. And in part, this is what motivated us to try to look for quantum algorithms for Kronecker coefficients. And yeah, something also interesting to note is that they are central object in a study of geometric complexity theory towards proving P not NP, but from an algebraic version. They want to show certain orbits of the determinant and the permanent polynomials are non-equivalent, and what they do is they look at these things as representations for the general linear groups. And the coefficients that appear there are Kronecker coefficients. So we have a quantum algorithm for Kronecker coefficients because, why? Because we know how to apply QFT over Sn and therefore over Sn times Sn. We know how to do generate phase estimation over Sn. So all we need to do is figure out how many times we need to repeat the sampling. And if you remember, equation 14 has the general cost of our algorithm, which is, I'm using n here to denote all of the costs associated with the quantum Fourier transforms and the control group actions and so on. And the thing on the right is the sampling cost, is how many times I need to repeat the run of the quantum algorithm. And this is the dimension of the ambient irrep of the irrep of the ambient group divided by the dimension of the irrep of the subgroup squared. And okay, so gamma in the case of our problem would be mu times nu. So d gamma is d mu times d nu, and d alpha is d lambda, and n is of the order of n to the 4. So our algorithm will run in time n to the 4 times d mu d nu over d lambda squared. Now, if we consider a special subcase of diagonal Kroneckers, since Kronecker coefficients are symmetric under any permutation of the lambda, mu, and nu, I can write this thing as g mu lambda mu, and you can see that mu and lambda basically mu and mu cancel. There's two mu's and they cancel in the expression 15, so you just get d lambda squared. So now you ask, when is this efficient? When is computing Kronecker coefficients with this quantum algorithm efficient? Well, you need d lambda to be polynomial. And it's the dimension of a partition. So the hook length algorithm gives us a way of computing dimension of Sn irreps efficiently. And one can show that the dimension is polynomial whenever the tail of the partition is fixed. The tail is all of the boxes that are below the first row. So if I fix the tail to be k boxes, then the dimension is of a lambda is order n to the k, and therefore the algorithm runs in n to the 4 times n to the k squared, which is n to the 2k plus 4. Instead, the classical algorithms recently derived, although also polynomial in the same regime, they are n to the 4k squared, in this case, plus 1. So just taking an example of k equals 3, there is a gap of order n to the 10 for the quantum algorithm versus n to the 37 for the classical algorithm. So even if the classical algorithms were not optimal, there is fair hope to believe this gap will stand improvements. We made it to the end of the talk, maybe a little bit beyond time, but let's wrap up. As I said, as I was telling you, we found these quantum algorithms to compute multiplicity coefficients whenever there is an efficient GQFT, and you can initialize maximal limits onto some rep H that you care for, and you can implement the group action over H. If you specialize in restricted representations, so H being restricted representations, then you can have like a routine for preparing the initial state by inverse SQFTs and so on and so on. We exemplified this with Kroneckers, but also Kostkas, Littlewood, and Plethysm coefficients can be instantiated as a version of our restricted algorithm. In that case, you need to take the ambient group to be Sn, one copy, and then G to be either Young subgroups, this product of two subgroups of SA and SB, and a Rath product subgroup. All of these subgroups give us the Kostka, Littlewood, and Plethysm coefficients. I just chose to exemplify just with Kroneckers. As I already discussed, the complexity has two components. One is the circuit complexity associated with implementing the quantum Fourier transforms, and the other one is sampling cost. And we illustrated the potentiality of these algorithms by discussing this gap that we find, and hints at a potential quantum advantage. With this, I want to Thank you for listening. Thank you so much. Are there any questions? In a sense, that's a probability, right? Yeah, totally. Like, yes. Okay, I see where you're pointing, and yeah, okay. Both Shor's algorithm and our algorithm depend on sampling from the correct distribution. Shor's algorithm uses these samples to solve a decision problem or a search problem. In our case, in that case, it's the hidden subgroup problem. You need to search which is the hidden subgroup or decide, is this the hidden subgroup or not? In our case, we're computing multiplicities. It's different. We're as you say, we're sampling and using the samples to estimate multiplicities. One could ask, and we are working in that, is there a version of our, like, accessing the same distribution that we access and we use to compute these multiplicities, can we also solve some decision problems or some search problems? It's a great question, and it's we are working on that. Is there a hidden subgroup version? Can we solve some hidden subgroup problems with this distribution? Basically, that's what we're trying to answer. So looking at the Kostkas, you mean? So a priori, you don't need to use anything because the algorithm is already there. Maybe using, so you want to use the theory of symmetric functions. Maybe you can find other algorithms, or I put it the other way around. Maybe you can use these algorithms to help the theory of symmetric functions. You know, I don't know. Maybe you can do stuff about like symmetric polynomials as like this is very suggestive that all of these coefficients appear as when you change basis of the ring of symmetric polynomials between, like, I don't know, elementary symmetric polynomials and complete homogeneous or power sums. So I guess there could be something there, but I don't know exactly. Totally, yes. Maybe this is something that you can actually, yes, that's a good point. Probably.